Hi, my name is George, lead mechanical designer at Toyota's first bumper division. My team and I have been working tirelessly to bring to you the biggest change to the Toyota Corolla since the 2018 model year. In the 2019 model year, the vehicle will not only have improved fuel efficiency, but it will also be at a reduced cost, all by one miraculous change: the bumper. The bumper in the 2019 model year Toyota Corolla will be made by a totally different process and different materials, through which we will do something that has never been done before: reduce cost and improve performance. To take you through the change in bumpers over time, and to help you understand how we've gotten to where we are today with our revolutionary design, NASA engineer and my good friend, Matthew.
Thank you, George from Toyota. I'm honored to be here. I work with NASA, the National Association for Safe Automobiles, where bumpers play a huge part, as you know. Bumpers existed on the very first cars as early as 1904. The first evolution of the channel bar was the double bar. It was essentially one channel bar stacked on top of another one. And this helped with collisions because often bars or bumpers would miss each other. After that came the biflex bar. It used the material's elastic properties to dampen the collisions. Then, for quite some time, the chrome solid bumper was widely used, mostly for its aesthetics and ornamental purposes. Finally, in 1968, the Pontiac GTO came out with a damage-resistant plastic bumper, and they advertised it by having a scientist use a sledgehammer against it. The Renault 5 came out later on, with the first completely plastic bumper. Since the Renault 5, all bumpers have essentially been in plastic. At this time, new legislation was imposed. For one, the car had to resist all damages at speeds up to 4 kilometers an hour. Borj Jerry, head of design at Toyota, will now speak to you about how Toyota is revolutionizing the bumper industry.
Thanks for that, Matt. Here at Toyota, we're all about changing the design game. The bumper has a couple components that we need to consider. Looking at the diagram here, there's a plastic fascia. Behind that, there's a foam or honeycomb layer used to absorb some of the energy when an impact does occur. After that is the reinforcing beam, and finally, the frame of the car. After our engineers cracked up some crazy code and incredible algorithms to find out where the biggest savings and improvements could be made, we determined that it was the reinforcing beam that had the biggest potential. Our objective was to minimize the mass of the reinforcing beam without compromising its safety and security for our passengers. So we wanted to put a material in with low weight and high strength. In Canada, vehicles must pass a stringent set of regulations to ensure they are roadworthy and safe. First, a pendulum test is done. A pendulum of equal mass to the vehicle hits the car on each of its 4 corners at 4 kilometers an hour. The next test that is done, the light pole test. Vehicles must meet the criteria that they can run into a lamppost or a fire hydrant at 4 kilometers an hour. Notice these vehicles here, those are not happy drivers. But Toyota cares. So all of our 2019 Toyota vehicles and forwards will be completely immune to any sort of lamp post collision. Toyota vehicles pass the test we've set in front of ourselves if there's no cracks or damages to the bumper, and if no fasteners or body panels come off, such as what you see in front of you here. With these tests and conditions that we've set in front of ourselves, our crack engineering team at Toyota began crunching the numbers and finding a way to create a totally new reinforcing beam, the likes of which the world has never seen before. We're tossing it back over to Matthew at NASA, and we're going to hear their report on how things went.
Thank you, Borj. Very cool. Matthew here at the National Association of Super Algorithms, and I'm going to take you through how we determine which material was best used in the bumper. We first started by determining the functional requirements. There are 3 main ones. For one, the bumper must mount to the chassis. 2, it should not protrude from the vehicle and should be nicely integrated. And finally, it should meet all the requirements that Borj outlined. Then, we determine the constraints. Firstly, it must span the front and rear end of the vehicle. It must pass all requirements that Borj outlined earlier, relating to the pendulum test and the barrier test, meaning it cannot crack, suffer from any cosmetic damage, or have any panels pop off after testing. And 3. The bumper must prevent any damage to any other component in the car. We also outlined the geometric constraints. As per the Toyota Corolla 2019, it must be 70 inches wide. 2. The bumper must be 20 inches from the ground and must be 6 inches tall. And 3. From the armature to the fascia, the bumper must be 35 centimeters wide. Although our super algorithms are quite super, we also have to consider other factors, such as resistance to corrosion, wear resistance, aesthetics, and minimizing damage to pedestrians. After stating these requirements and constraints, we made a few assumptions. We assume that the bumper operates solely in its operational zone, for the foam that is. We assume it compresses to 40% of its original length during the 4 km/h test. For test 1, other assumptions were made. We assumed the lamppost was a point load applied perpendicular to the armature in the very middle of it. We assumed compressive stress would be less than the compressive stress during the corner test, so we did not consider it as a failure method. We also assumed that the bumper is a simply supported beam at each end, where the distance between both ends is 65 inches. For test 2, we considered that the pendulum was applied perpendicular to the corner and that the same amount of foam compresses in this situation as with the lamppost test. We also considered that the bumper is constrained from within, therefore we're considering solely the compressive strength of the bumper. We equally assume that the bumper is anchored during the test and will not roll or move when the pendulum strikes it. Using the simple kinematic equations, we can then determine the net force that's acting on the armature. We can determine the minimum compressive strength of the material. In this case, it happens to be 205 kilopascals. As mentioned by George and Borge, we're here to reduce mass and make savings when it comes to cost. Those will be our objective variables, and our free variables will be the thickness of the armature and the material properties. Using this formula, which describes the deflection of a thin plate, we can use this to determine the MPI. In other words, we have to maximize Young's modulus over the density. This is just our first MPI equation, but there are others. The second is considering the yield strength of the material. Or in other words, we have to maximize yield strength over density, and the slope of the line will be 2. With these 2 MPI equations in mind, and one other constraint being the compressive strength, we went to CES EduPack to plot all this data. We plotted Young's modulus versus the density. We then plotted the line with a slope of 3. Plugging in all the values into the equation, we solved for a minimum MPI. For stage 2, we plot the yield strength versus the density. We plot the line with a slope of 2. Using the same method as before, we find a point and we plot the line accurately. Finally, plotting the Young's modulus versus the price times the density gives us an MPI that will allow us to minimize cost. It's important to note that we use a safety factor of 2 in all these equations. The top candidates from this graph are notably aluminosilicate, certain woods, PP Homo, and foam. It's interesting to note that cast iron was the runner-up in terms of materials. It was very inexpensive, had a high Young's modulus and a high yield strength. However, it was very dense, putting its final mass at just over 26 kilograms. The final cost, however, was $9.6 per bumper USD, about 2/3 the cost of the magnesium bumper. However, the magnesium bumper only weighed 8.3 kilograms, making it much more interesting as a whole. After determining that all these materials were not suitable, we finally settled with magnesium commercial purity. Magnesium, being a metal, was a clear winner for us. It's strong, durable, elastic, and just great all around. Inputting magnesium's material properties into our MPI equation, we determined that the mass of the reinforcement beam would be slightly greater than 8.3 kilograms. The final cost of the reinforcement beam would be just over $15 US. The thickness would be 1.5 centimeters, which is reasonable. It's also extremely machinable. In fact, it's the most machinable metal in the automotive industry. However, there is a drawback. Magnesium cannot be cold worked or hot worked or pressed into shape. It must be cast. But we'll deal with that later. Once again, magnesium being a metal, mounting options for the chassis are not an issue. It can be bolted, riveted, or welded. The only other drawback to magnesium is that it is stress, corrosion, cracking susceptible. But once again, there are solutions to that problem. And our friend Porridge Barry will help with that.
Thanks for that intro, Matt. George Harry here. Porridge Harry here. Porridge Harry? George, Porridge Harry, Porridge Harry. Thanks for the intro, Matt. Porridge Harry here, materials
and strength
specialist. Here at Toyota, we only select the best materials for our vehicles. All of our magnesium ingots come from Alibaba. Being a pure element, magnesium cannot be hardened in many of the ways an alloys can. Solid solution strengthening, dispersion strengthening, precipitate hardening, quenching, and tempering are not possible without the presence of a second species. Magnesium is also one of the few metals that cannot be cold worked. Though this might seem like a concern, even in its base form, magnesium outperforms any reinforcement bars that we presently have in our vehicles. The manufacturing process for the reinforcement bar consists of first melting the ingots. The melted magnesium is then cast into very large sheets. The magnesium sheets are then bent into the appropriate U-shapes. At the corners, magnesium has a high internal stress. This leads to high susceptibility of stress-driven corrosion, a huge problem for magnesium. To alleviate this issue, the corners of the magnesium beams must be annealed. The internal stresses will then dissipate and the probability of stress-driven corrosion plummets. Magnesium is susceptible to corrosion in other forms as well, not only as a result of stress. Magnesium and its alloys are susceptible to corrosion in neutral and acidic solution. Corrosion is a concern on all faces of the reinforcement beam. As the reinforcement beam is out of sight, the use of inhibitors and seals on any surfaces will do great at preventing moisture from touching and corrosion from forming. Most vehicles are made of steel frames, and the reinforcement bars touch them. To prevent corrosion due to dissimilar electric potentials, galvanized steel bolts can use a silicate seal and polymer washers to minimize the chances of contact corrosion. Through the use of seals, inhibitors, and insulators, the reinforcement bar can stay corrosion-free, regardless of the climate. Through the steps that we have taken here, we've ensured that we've improved the fuel economy and mass of our vehicles. We've reduced costs and improved safety. Here at Toyota, we always strive for the best, and that means being number one to you.